So here's question 3, the first circuit problem, and I'm going to solve this circuit. So the first step, and this guides you through it, is to add all these capacitors to get a single equivalent capacitor. So if you know how to do that, or think you know how to do it, just pause the video and do it before you watch what I do. If not, I'll walk you through this one. So the first step is, this is in series with something that's not simple. So you have to simplify this to a single capacitor. And since these two are simply in parallel, you just add them. So add those two and see what you get and come back. So you added the 16.1 to the 23.9, and it comes out to exactly 40. So a single capacitor of 40 is exactly equivalent to those two in parallel. Now we got to add these in series. So we have a 35.9 and a 40, and so it's going to be, I know from experience that it's going to be smaller than the smallest one. And if they were both 40s and they were in series, you would get a 20. So I can guess that this is going to end up being something like a 19 microfarads. So add those two in series and see what you get. Okay, so you know when you're adding in series, you add reciprocals. So 1 over 35.9 plus 1 over 40, which is those two together. And that's 1 over the answer, so you have to invert that again. So that's why I write it this way. So if you take 1 over and then invert it, you get 18.92. Make sure you can do that math. And that's what I said, it would be around 19. So the total of all three of those, if you put a single capacitor of 18.92 and replace these three, it's going to be the same thing. So, but that's the sum of these. What we really want to find out is how much charge is on each one and what's the voltage across each one. So we have to start with this one and work our way backwards. So find out how much charge the battery would put on a single capacitor of this amount. So we're calling this C total or C123, and the charge on this one is going to be what we call Q total. So just use your equation and calculate that. Okay, to get the charge, we use this equation that relates charge, capacitance, and voltage, and we solve for charge. So the total charge is going to be the total capacitance times the total voltage. So we multiply those together and we get 238.39. And the answer is going to be 238, but we save those extra digits for calculation purposes. The last question, there's a misprint which I corrected. What is the total equivalent energy delivered by the battery stored on the three capacitors? So that's U total. So on your equation sheet, you'll find the equations for energy. U C for capacitor, and it's 1/2 Q times V. Now, since we have this relationship, this can also be written two other ways, which is sometimes useful: 1/2 CV squared or 1/2 Q squared over C. Those are just derived by using this equation. So since we have the Q and the V, we'll use this equation, 1/2 QV, and that gives us the result. That's the answer with extra digits, so you report 1500, and that would be nanojoules. Yeah, I need to fix that. That needs editing. Now we have to step our way back and find of this charge how much is on each capacitor, and of the total voltage, how much voltage is across. Remember, we're always measuring voltage by putting the probes on each side. We're measuring the voltage across. And so if there's 12.6 volts across all three, there has to be less voltage across C3, and capacitors in parallel are in parallel, so that means they have the same voltage. So what you should know is that the voltage here plus the voltage here has to equal 12.6. And the charge is even a little more complicated. Since the battery is sending out 238 nanocoulombs of charge, it all has to go here, and it all has to come back from there. So this is what you have to know, is that we do know, because this is in series with the battery, that it has to have 238 nanocoulombs of charge. And what we know is that there has to be 238 nanocoulombs of charge split between these two, because they were in parallel, right? Because if we remove 238 charges from here, some from here, some from here, so that's what we have to figure out. So since we know that all of the charge leaving the battery has to go here, we can write down that on C3, the charge is 238. And once we know the charge and we know the capacitance, we can find the voltage just using, C equals Q over V. So V is going to be Q over C. But be careful, we're going to get V1, the voltage across this capacitor, is going to be Q1 divided by C1. So do that and see what you get. So Q1 is that, for reasons I explained, not so obvious. C1 is pretty easy. That should be C3, excuse me. I screwed up. This is all C3. So we're finding the voltage across 3, the charge on 3, and the capacitance of 3. And what I said was the charge on 3, is the full charge from the battery. So that's that. And the capacitance of 3 is 35.9, and that gives us, and this is microcoulombs, and nanocoulombs and nanofarads, so we get volts. So now we know that the voltage across this capacitor is 6.64 volts. And that makes sense because the battery is 12 volts. So about half of it is there. The other half is going to be across these two because they're in parallel. So if we simply subtract this from the 12.6, right, the remaining voltage has to be on the other one. So let's do that subtraction. Okay, so I did the calculation, 16.1 times 5.96, the voltage across 1, and that gave me 95.95 nanocoulombs. And then C2, 23.9 times the same voltage, because they're in parallel, gave me 142.4 nanocoulombs. And notice, I can check whether I'm right or not. If I add these two together, right, the total charge there has to be equal to the charge here. And that's what I'll get. I'll get pretty close to the, except for rounding, the 238.39. And so now I know that I can be certain that all these values are correct. And so I just leave it to you to calculate U for each one of those, simply using that U1 is going to be 1/2 Q1 V1, and so on for 2 and 3. And those three numbers, the number you get here, here, and here, added together, should add to that, if you don't make any mistakes. Okay, that completes this circuit.